Hello and welcome back to this course. So we were looking at the effect of catalyst on the performance of whether it's a fuel cell or an electrolyzer. So we saw how anodic current and the cathodic current varies with the usage of a better catalyst. So for example, if you have taken platinum in case of fuel cells, so as we can see for a given anodic current IA, like we can see here. So we can see that for a lower overpotential, we can expect to have a same current compared to that of nickel, which will have to invest eta Ni of overpotential in order to get the same current in the circuit. Same also goes with the in case of electrolyzers. So we can see that for cathodic current IC, in case of iridium, we have to invest overpotential of eta subscript IR, and this eta subscript IR is far less compared to eta cobalt for the same cathodic current in the circuit. So that is what we can draw as a conclusion, that with a better catalyst we can get better our performance. In case of fuel cell, it will be an anodic current, and in case of electrolyzers it will be the cathodic current. We also saw in case of transfer coefficient that how it plays an important role in tuning this catalyst to prefer the said reaction. So for example, if we want to favor forward reaction, in this case it is hydrogen getting oxidized to protons and electrons. So if we see that if alpha is chosen as 0.25, as we can see this purple color line. So if alpha is chosen as 0.25, again we can see that for anodic current we will get same or a better performance compared to the other transfer coefficients. So this will be eta 0.25, in other words eta corresponding to transfer coefficient 0.25, this is eta 0.5 and this is eta 0.75. So as the transfer coefficient is increased, we have to invest more energy to get the same current in the circuit, that is anodic current. Same principle is also applied in case of electrolyzers. If we can see, if we increase the transfer coefficient, that is 0.75 from 0.25, we can see that we can get similar cathodic current for a lower overpotentials. So as we can see here, so the overpotentials here, this is for 0.75, this is eta 0.5 and eta 0.25. So higher is the transfer coefficient, better will be the cathodic current. In other words, that particular catalyst will prefer the reverse reaction, that is in this case it will be protons and electrons getting reduced or to hydrogen, gaseous hydrogen. So that will be preferred when alpha is higher. So let us move on and see what happens when this eta is fairly small and fairly large. So that is what will lead to Tafel equation. So let me write a first case, that is eta is very small. So when the eta is very small, we can write this NF eta is also very small. So that leads to, so mathematically we can write this as, so let me write this as, if x, I can assume this as an x, so this entire quantity is x. So if x is small or rather very small, so we can write this x as e raised to the x as 1 plus x. Okay, mathematically we can write this e raised to x as 1 plus x. So what will happen to our reduced form of Butler-Volmer equation, which is I equals I naught e to the power 1 minus alpha and f eta by RT minus e to the power minus alpha and f eta by RT, right. So I can replace this e to the power terms by 1 plus x. So let us do that. So it will be 1 plus 1 minus alpha and f eta by RT minus 1 plus minus alpha and f eta by RT, right. So let us see what happens here. Let us resolve this. So I equals I naught n f eta by RT minus alpha n f eta by RT plus alpha n f eta by RT. That 1 gets cancelled, and this is what we have, and as you can see this gets cancelled. So, what we have is I equals I naught n f beta by RT. So, if we look at this expression, when eta is very small, so typically we are operating, so when I say eta is very small, we are somewhere here, and this eta is somewhere around 5 to 10 millivolts. Okay. So, it is a very small number. So, as we can see, this is in the form of V equals IR. This is in the form of V equals IR. And so, and this, if we rearrange these terms basically, so we can write the same expression in this form. So, in that eta is called as activation overpotential. So, eta equals, so eta now we are going to write as eta activation, and if I rearrange these terms, it will be I times RT by I naught and F. So, now this is in the form of V equals IR. So, let me rewrite that. So, then that eta activation becomes I times CT, whereas this CT is called as charge transfer resistance. RCT is a very important property of the catalyst to basically transfer the charge, that is transfer the electrons to or from the diffusion layer. So, higher is the RCT, inferior will be the catalyst, and that is why it is always better to have this RCT as low as possible in order to have better kinetics at the reaction sites. So, let me write that what is the RCT? RCT is basically T by I naught n f, and if you can look at this RCT is inversely proportional to I naught. In other words, higher is the exchange current, lower will be the RCT. So, and as we have seen this before, higher is the exchange current. In other words, it will be that catalyst will be performing better, and this is one of the reasons why higher exchange current leads to better catalyst. So, this is with respect to the RCT and how it looks like in actual fuel cells. If I have an IV curve, so if you are now focused at very lower etas, so eta is typically very low etas. So, if I zoom here, it will be something like this. So, this is your, let us say, open circuit potential, and if you are operating at this E, this is your eta activation, which is typically 5 to 10 millivolt. So, this eta activation is, as we can see, there are two reactions happening at the respective electrodes. We also have activation on the anodic side, and we also have activation on the cathodic side. Sum of these two basically leads to total activation overpotential. So, if I try to simplify this using the conventional reaction barriers, so it will be like this. So, initially it is at the equilibrium. So, when we get the imbalance in the system and we want to favor the forward reaction, So, this is our first eta activation, let us say anode, and similarly we also have, let me draw it with the different color for secondary electrode. This is eta activation cathode, and as you can see, sum of these two basically, this is at the equilibrium, right. So, this is where you can see that both of these activations get added. So, we have total eta as eta activation anode plus eta activation cathode. So, this is total eta activation. So, both of these activation overpotentials get added. The magnitude will be different because as you can see, this is our forward reaction H2 giving 2H plus 2 electrons, and here we have half mole of oxygen plus 2 moles of protons plus 2 moles of electrons combining to form water. So, this is our third 2 to 3. So, as we can see 1 to 2, that is forward reaction in the on the first electrode, that is anode, is fairly simple compared to the forward reaction that is happening on the second electrode, that is cathode in case of fuel cells. And as we can see, the second reaction is far more sluggish compared to the first electrode, and or that is first forward reaction of the anode, and that is why the activation overpotential of the first reaction, that is 1 to 2, the hydrogen oxidation, that overpotential is far smaller compared to the activation overpotential of the second reaction, which is the reaction that involves reaction with the oxygen, protons and electrons. So, if I try to show this graphically, this is the reference. So, as we can see, this will be, let me use these colors, this will be, this is our eta activation, that is for anode, which involves H2 giving 2H plus 2 moles of electron. And how does it look like for the cathode? Cathode, as I mentioned earlier, the activation overpotential for the oxygen electrode is far more compared to that of anode. So, it will have more overpotential. So, this is activation of the cathode, which has oxygen reacting with protons plus electrons to form water. And as you can see, sum of these two basically leads to the final curve, and that is how we get this curve, and this is the final IV curve that we get at the when we characterize the cell. So, this curve is basically nothing but the start of your characteristic curve. So, as we can see, this is the same, okay, it is the same, and this basically has at any given point, it is basically sum of your eta activation is nothing but sum of respective overpotentials at anode and cathode. And as we can see, activation of anode is far smaller compared to activation of activation overpotential of the cathodic reaction, and that is how the activation overpotential at respective electrodes is found out, and that is how it appears to be. So, for a given hydrogen oxygen fuel cell reaction, activation overpotential of the anode is far smaller compared to that of the cathode, and in other words, if I simplify this, the activation overpotential or the energy that is invested in forwarding the reaction at the cathode dominates in terms of the energy invested compared to that of anode. Okay. Let us go to second case where eta is fairly large. So, second case when the eta is very large. So, very large means eta is typically more than 52, or it is in this range 52 100 millivolt, it is typically more than 50 millivolt and around less than 100 millivolt. So, let me write typically for fuel cell. For fuel cell, now this eta is positive, as we can see it is eta is E naught minus E. So, E naught is always greater than E. So, eta is positive in case of fuel cell. So, let us write this Butler-Volmer equation one more time, a simplified version of Butler-Volmer equation. So, we have e to the power 1 minus alpha nf eta by RT minus e to the power minus alpha nf eta by RT, right. So, what will happen if this eta is positive in case of fuel cell? This will increase, right, this factor will increase and this factor will decrease. This factor will decrease as your eta increases, right. So, in other words, the second factor which is going to decrease, we can neglect that and we can write this same equation one more time as I equals I naught e to the power 1 minus alpha and f eta by RT. So, in other words, e to the power 1 minus alpha and f eta by RT equals I by I naught. I have just rearranged the terms. So, let us again rearrange the terms and write it for eta. So, that is RT by 1 minus alpha and f ln I by I naught, right. So, if I simplify this, RT by 1 minus alpha and f ln I minus ln I naught. So, this is again eta. So, if I expand this bracket, I get minus ln I naught RT by 1 minus alpha NF plus RT by 1 minus alpha NF ln I, right. So, if you look at this expression, it is I naught for a given catalyst is fairly constant, R and T and F alpha are also constant for a reaction. So, this first term on right hand side is constant and the relation is between eta and I. So, this is a like sort of equation of a line. So, I can write this as this is in the form of equation of the line. So, eta equals A plus B ln I, and this eta is again your activation over potential when eta is large, and that is why this equation is called as Tafel equation. Let me write this in different colors. So, this is your Tafel equation, and this term specifically RT by 1 minus alpha NF is the slope of that line. So, eta activation is T by 1 minus alpha NF ln I by I naught. It is the same line same equation that I have written, and this Tafel slope is B if we compare that with the line of equation. So, that is B, and which is nothing RT by 1 minus alpha NF. So, what does it signify? And we can understand the significance of Tafel plot, Tafel equation if we draw the relation between the current and the overpotential. So, let us do that. So, this is again positive eta, negative eta. This is again, now this time we are going to plot it on, instead of simple anodic and cathodic currents, we are going to plot it on logarithmic scale. So, it is ln of anodic current, this is ln of cathodic current. So, we will draw using different color. So, as you can see, this, for when eta is fairly large, it appears to be in the form of straight line, right, till a certain point. So, and if we extend this line on the vertical axis or axis that crosses the anodic current or cathodic current vertical. So, this is the point where eta is 0. In other words, the external current that is flowing in the circuit is 0. So, this is the value, this corresponds to ln I naught. Okay. So, when the eta is 0, whatever current that we get from the equation is your exchange current or ln of I naught, and then which can be eventually converted into the relation that gives out the exchange current value. And this is the slope, as we can see, this is the slope, which is RT by 1 minus alpha NF, which is the B, term B from the equation. So, this is for the case where eta is fairly large. So, this is the second case, eta is large. So, in that case we can write this slope as the same, RT by 1 minus alpha NF. What is the case when eta is small? So, as we can, if you recall this equation, it says that eta is directly proportional to I. So, in that case, eta is directly proportional to I. So, in other words, it is a straight line which passes through the center. So, we draw with a different line. This is the zone where eta is small, and from this point onwards, the eta, when eta increases, this is eta is large, right. So, this is typically we are operating around 10 millivolt or 20 millivolt or so, and when eta is large, around 30, 40 or 50 millivolt or even larger, then we say that it is a second case and it will be in the form of the straight line. This appears to be for the fuel cell. This is for fuel cell. How does it look like for the electrolyzer? So, let me use the same colors one more time. So, this is again so this will be ln of I naught, and for the cathodic current, and if we again extend this, so this is again the zone where eta is small, and when eta is large, we get straight line connecting or relating the cathodic current and the respective overpotentials. So, we have to understand here that eta is negative in case of electrolyzers and eta is positive in case of fuel cell, and straight line basically if we extend it to the vertical or the axis that takes care of the anodic and cathodic currents, we get the exchange current, and that value of exchange current can then further be used to find out the RCT also. And if I start off, try to draw trying to understand what is happening at lower overpotentials, same colors. So, if we look at this, there is a change in the slope. So, that change goes like a goes like this. So, this is called as Butler-Volmer forward current, right, and as we have already mentioned, the slope this is the slope of the line, and this will be ln I naught. When eta is 0, the value of current that we get is nothing but the exchange current. So, to summarize, if you want to increase the net current in the circuit, to summarize, let me write to increase the current in the circuit. So, why do we want to increase the current in the circuit? As we know, the very function of a fuel cell is to deliver maximum power, and maximum power comes when we are drawing more current from the circuit. So, if we want to do this, what are the different ways? First, we have to do is the increase surface concentration, right. So, in other words, this CO0T has to be increased. And how do we increase this concentration? We can increase the pressure. So, if the pressure is increased, then the availability of this species at the respective catalyst sites will also be increased, and specifically with respect to the oxidant, we can use oxygen instead of air. And the reason for that is, if you use air, which typically contains 20% of the oxygen, in other words, we are supplying 80% less oxygen at the reaction sites. So, if you want to increase the reaction rate, we have to supply oxygen, because that is what is being used in the reactions. So, if you supply oxygen, that will be 5 times more compared to that of your air, and that is why the reaction rate will also be increased if the oxygen is used instead of air. Second case is you have to decrease the activation barrier. So, which is your delta G1 on delta G2 for the respective reactions, whether it is a forward reaction or reverse reaction at the respective electrodes, that has to be decreased. So, how does this reaction barrier depend on? It depends on that MH bond. So, this activation energy delta G in general depends largely on this M chemisoft H bond. So, how is this hydrogen chemisoft on this metal nanoparticle? This bond decides what is the activation energy of that particular reaction. So, that is why, in other words, selection of this metal M, or this only M, plays a very important, or is very important. So, what are the 3 different cases, or the different cases? This M dot 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 H is as a strong bond. Okay, let us take this example. So, if this soft hydrogen is strongly bonded to the metal nanoparticle, so it will not release that protons very quickly in the electrolyte. So, in other words, we are basically decreasing the rate of the reaction. Second case is this MH is very weak bond. So, if MH is a very weak bond, in other words, hydrogen will find very difficulty in getting chemisoft on the metal nanoparticle and the further reactions will not take place. So, how this metal H, that is MH bond, it should be intermediate bond. So, that is very important. So, it should neither be very strong, neither be very weak bond. It is an intermediate bond. So, it should not have very high affinity towards M, nor it should not have any less affinity towards the metal nanoparticle. So, if it has an intermediate bond, the reaction rate will be increased, and that is one of the reasons why platinum is used in most of the fuel cell reactions, because this platinum very finely has this bond satisfaction with respect to chemisoft hydrogen, and that is why the swiftly taking of this electron from hydrogen is very nicely done by platinum, and that is where it surpasses the other catalysts. What is the third, we can say, step to increase the current? So, this we can increase the temperature. So, if you can increase the temperature, so as temperature increases, the current increases, because this thermal energy, basically thermal energy in the form of increased temperature is made available for the reactions. And second, so the last one is basically increase the reaction sites. So, how is this the reaction site can be increased? So, we know that so if you take a smaller fuel cell, let us say this is 5 centimeter square, and if you take a 50 centimeter square cell, so number of reaction sites here at the surface of the electrode will be say X, and here the reaction sites at the reactions basically at the catalyst and the electrolyte interface, let us say Y. So, as the area of the electrode is increased, the number of reaction sites will also increase. In other words, this the reaction sites. And that will lead to more reactions happening simultaneously at the electrode surface, and that is why if the electrode area is increased, we can expect more current to be generated from that particular cell, and that is one of the reasons why we can, or we have to increase the reaction sites. In other words, we have to increase the area of the cell. Okay. So, we will stop here and we will take on with numericals in the upcoming class. Thank you.